You will find I don't have the draft notes up just yet because I tried to add some references and I crashed text. So I'll put those up right after the lecture when I sort out the references. Right. But okay, so today's lecture is different from the last two in a couple of ways. So I'm going to be explaining about how infinity modular operads, why I even started thinking about them in the first place, and how modular operads relate to Grothendieck-Teichmüller theory. So I will also say that one other thing that is a little bit different in today's talk is that I'm going to have to lie to you at a couple of places. I'll let you know where the lies are, but I mean, I'm going to make things sort of almost the same equal, and I'll tell you exactly where those things are. So that it's not really a lie, but it's hard to get all the fussy details here. All right, so let's start. I'm going to start on the first with sort of what I called a really fast introduction to a lot of really cool math. So I want to start by explaining what people mean, or at least what I think people mean when they say Lego-Teichmüller or Grothendieck-Teichmüller theory. So we'll start with sort of letting Gal Q be the absolute Galois group of Q, right? So this is the topological group of automorphisms of the separable closure Q bar over Q, which fix Q. So the big one. And this is a giant profinite group. And a sort of first goal, right, you might have if you wanted to study this group is write down an element of the group. That seems like a reasonable request. But what we learned yesterday, or at least rapidly had thrown up in front of you yesterday, was that if if this group is profinite, writing down an element in that group would require us to describe the image of G in each of the finite quotients, right? So the profinite completion was this limit over a big tower of finite quotients, and we want to write down the image of G in each of those. But we don't know what the finite quotients are of the absolute Galois group. Right? So this is a very confusing group, and we don't really know how to write down elements. So, and I'm being rather loose with this, so maybe I apologize, but the Grothendieck part of Grothendieck-Teichmüller theory was a program by Grothendieck that said you should try to identify elements of the absolute Galois group Q with pairs of an integer and an element of the free group. So here, this is the profinite completion of the integers that we saw yesterday. Just the invertible elements, so if you need a definition. And here, this is the completion of the free group on two letters. And I'm always going to use X and Y for those variables. And there's a little check here, but that technically means, so if you're in the audience and are familiar with this, the derived subgroup of the free group. But if you don't know what that means, you can completely ignore it. Okay, so the first thing we understand, this integer, so this is just the cyclotomic character. So we saw this in Geoffroy's talk, I think it was the one yesterday or the day before, one of Geoffroy's talks. He talked about the cyclotomic character as giving the action of the Galois group on the roots of unity. So this is a well-understood integer. The hard part, sort of the Teichmüller part, the hard part is the description of F. So how do we get this element in free group? All right, so the idea is that since F2, this profinite completion of F2 is the fundamental group of the moduli space. So again, here's one of the things where I'm being a little bit loose. I'll be more specific later. As a fundamental group of the moduli space of genus 0 with 4 marked points, that I should understand, the idea is that you should understand the actions of the absolute Galois group on the moduli space in order to find some sort of necessary and sufficient conditions for FG to have come from, for this F to have come from G, okay? So we wanna, the summary is, the idea is you wanna study how the absolute Galois group of Q acts on the moduli spaces in general, so all of them, for all G and all N, and see if we can figure out some conditions for an element of the free group to come from an element of the Galois group, right? And this approach is somewhat successful. It's yielded some necessary conditions, and nobody really knows about sufficient conditions, as far as I'm aware. I'm not a complete expert in arithmetic geometry, so if someone wants to jump in and correct me on this part, it's fine. So that's my really fast introduction to where we're going. So the Grothendieck-Teichmüller group, so the profinite Grothendieck-Teichmüller group, is some intermediate object, okay? It's going to live, so it's going to contain the absolute Galois group of Q, sits inside of it, and there's some relation, as we'll see, to the collection of all the moduli spaces, right? So it's this intermediate object, but it's a nice group, and I'm going to show you in a second. It has a, I mean, it's still enormous, profinite, and complicated, but it has a presentation, so we know what elements in GT look like. Okay, so let me start with a little bit of notation, so that I can define GT. And I'm going to give you a definition of the Grothendieck-Teichmüller group, but you won't need to like memorize it. I'll bring it back every time that we need it. So just some notation. So given a homomorphism of profinite groups, so I guess I'm missing a little hat here. So where I map the generators of F2, so the X and the Y, to two generators of G, so A and B, we're just going to write F of AB, right, for the image of this word F, but now in the letters A, B, right? So for example, if you have the identity map from F2 to F2, you're just going to write F of X, Y, because X went to X and Y went to Y. If you take the map from F2 to itself that swaps X and Y, then you write F of Y, X, right? That's what this notation is supposed to be. So we can define this group. And like I said, you don't need to memorize this, but we'll go through it. It'll be around. All right, so this is a group that's defined as pairs of lambda f. So lambda is an integer and f is a word in x and y, possibly infinite word in x, y. And we're going to take the subset of those pairs, which satisfy the property that if you take x to x to the lambda and y to f inverse y to lambda f, you get an automorphism of f2. So we're already taking a little quotient. And then we're going to impose three relations. So the first one is a type of symmetry. The second one is a hexagon. And the third one, which may look a little bit unfamiliar to you, the way I've written it, is a pentagon equation. And when I write hexagon and pentagon, I really mean the same hexagon. Oh, I always misspell hexagon. Hexagon and pentagon equations from braided monoidal categories. They're just in particular, the third one is given slightly differently because I want to be talking about it today as something that's happening in a mapping class group. And we'll be coming back to that more. Okay, so, okay. And it was sort of, this group was introduced by Drenfield, where he described the injection that it should contain the absolute Galois group of Q. And then it was proved by Ihara that there is actually an injection of the absolute Galois group of Q into GT. So it's sort of this intermediate object that we know how to write down. Okay, So now we can extend our idea and we can ask, how does GT act on the moduli spaces? Okay, that's where we're going here. Okay. Now, I'm talking about moduli spaces, but for the last two talks, I've only been drawing pictures of Riemann surfaces, and that's going to continue. Oh, this is not my best picture, but I'm learning. So the main object we want to study, right, are the moduli spaces, so MGN, because they, in some sense, contain all of our algebraic information. But I want to talk, I've been talking about and drawing surfaces, and there's a reason for that. That's that points of the moduli space are isomorphism classes of these Riemann surfaces of genus G with n boundaries. All right, so I'm going to write sigma Gn bunch for throughout the talk for a Riemann surface with n boundaries. And I'm going to assume a few things that aren't super important, but might as well have them. So my boundaries will all have a collar. Which is a little copy, you know, some little interval floating around. I guess I could use a highlighter. Doop, doop, like around that. Floating around each boundary. And I'm going to assume that they have a label. You don't have to do this. I'm just telling you that I'm going to be thinking of this all the time. So I mean that I'm going to be secretly thinking that these things have numbers. 1, 2, 3, 4. And this is right, an example of a sigma 1, 4. Okay. So if points in the moduli space are surfaces, you can in fact check that a loop at it, like if you fix a surface, and I'm just going to leave the, okay, I'll put a Gn. I might forget to put the Gn if it's just an abstract surface in the moduli space. So if I fix one point, and I can look at loops, loops in the moduli space up to homotopy based on that point. Right, and this will be essentially what are loops in the moduli space based at up to homotopy. These are going to be precisely diffeomorphisms. Yeah, so they're going to be diffeomorphisms that are at least those which are homotopic up to those which are homotopic to the identity. Right, so and again, so here's one of the things where I'm lying. You have to be a bit more careful when I say something like this, right? So diffeomorphisms up to sort of those homotopic to the identity. Right. So what we can get from this observation is that if you look at a profinite mapping class group, so here I mean the profinite completion of the mapping class group. What is that? That's diffeomorphism. So I'm going to mean by mapping class group, I'm going to mean orientation preserving diffeomorphisms. So that's the plus. And I want them to respect the collars. So fixing, that's this little thing that I hopefully carry through the whole lecture. But if you don't know what that means, you can just ignore it. So these are orientation preserving diffeomorphisms that are like fixing collars. Well, I guess preserving labelings as well. And these can be identified with the fundamental group here of the mapping class group at this base point. So here, here's one of the lives, right? So this is technically, this is the sort of orbifold. Pi. So sorry, not pi I, pi 1. So I mean the orbifold fundamental group here. So, okay. So going back, putting everything together, what am I trying to do? So I want to know how I've moved from the Galois group to GT. I want to know how this acts on this moduli spaces. Well, and so we can actually look now, I want to know, maybe not on the moduli spaces, but the fundamental groups. Right? But I can instead actually look at what's happening at mapping class groups and then pro-finitely complete. Right? So I'm going to look at mapping class groups because I kind of understand these better. I'm not saying that everyone does, I'm just saying that I happen to like them. Okay. So that's why we're going to go down to surfaces. And in fact, we have quite a lot of control over the mapping class groups. So it's a theorem of Hatcher and Thurston from the 80s that the mapping class group has a nice presentation, right? So the generators here, what I've written as alpha 1 through k, these are Dane twists. So these are a diffeomorphism that looks like twisting around a particular circle embedded in the surface, right? So if I have a circle embedded in the surface and I have a Dane twist. So in particular, I have one generator for each of these boundaries, which you can think of as a copy of Z. So it's like a full, like, you know, I twist around, I don't know, think of like a corkscrew around each one of these boundaries. So there's a bunch of copies of Z. And then I'm not going to tell you what the relations are because we're not going to use them in this talk. But if you just want to know, so this stands for like the standard braid relation. D is for donut and L is for lantern. And I don't think C has an interesting name. It's just written as C. Maybe it does and I forgot it. But all right, so we have this nice presentation. So I'm not going to use in the talk that there is such a presentation. I'm going to use in the talk how they proved that they had such a presentation, like the proof of where this presentation comes from. And what that relies on is the notion of a Pants decomposition. So what Hatcher and Thurston did was they, described the idea that you can decompose every surface of genus G with n boundaries into with a maximum Pants decomposition. So what is this? It's a collection of simple closed curves. If this is new to you, I just mean embedded circles. That cut, if you were to cut along the pants, along these circles, you would get pairs of pants, right? So a surface of type 0, 3. So literally, I guess it's an upside down pair of pants, right? So here's one example, right? I can cut here along these two red lines, and you can imagine if you had some scissors and you chopped this guy up, you would have two pairs of pants. So the two circles there are the pants decomposition data. And I could also probably slice this guy up in another way, but I don't want to mess up my picture. So there are more than one. It's not unique on all of these pants. So there are more than one. There are many on each surface. Okay. And actually in this talk, I'm going to introduce to you a new modular operad that actually uses quilted pants decompositions. So I'll try not to draw too many of them because it's really hard for me to draw. But a quilted pants decomposition, as far as I know, this is introduced by Nakamura and Schnetz, which I'm going to misspell. Mora and Schnetz in this paper. So what is a quilted pants decomposition? So in addition to the pair of pants, we're going to sort of cut up the pants into some hexagonal pieces. So on each circle of a pants decomposition, so note that in a pair of pants, right, the boundary circles count as parts of the pants decomposition. You add 2 marked points, which we call vertices. And then between, we have 3 seams. So you can connect these seams in some way. And so it's 2 marked points and 3 seams on each pair of pants. And that breaks up the pair of pants into 2 hexagonal pieces. Right, and so there, again, these are not unique, and this is going to go badly, but right, I could have something weird like that, right? So you can have different seams as long as they connect the two boundary points. I think it's enough data. So just to put that, just to reiterate, what is the quilt, right? So first you have the pants decomposition, and the quilt consists of 2 marked points, which you call vertices, for every circle.
Sorry,
oh,
Marcy,
sorry, sir.
There's a question here. Maybe you can come.
Yeah.
Can these curves intersect the ones that you drew before?
These, which ones, the pants or the quilts? These ones?
On the right hand side, yeah.
Yeah, they can, okay. Within some rules, yeah. Yes. What I drew there, I think, is fine. Yes. Maybe. Yeah. Right. So it's 2 marked points called the vertices, and then 3. Oh no, sorry, they can't, because I just wrote down the definition behind disjoint lines. So what I wrote is, it's not a good drawing. We'll put a X on that one. Sorry, I was supposed to curve the top one around the bottom, but we'll just sorry, 3 disjoint lines between the vertices. And so it like slices, you have to end up with 2 hexagons. Like the key is however you cut it up, you need, the result is 2 hexagons for every pair of pants. Okay. Okay, so the good thing about the quilt is that it's completely determined by, first you give a pants decomposition of the surface, and then if you have to just mention what the vertices and seams are. So it is a lot of extra data, but it's not, you don't have to be able to draw it every time, let's put it that way. It's very good for me. I'm not that kind of topologist. Can't draw these pictures. All right. So something I want to convince you of is that, and it probably don't need much convincing in this crowd, is that Pants decompositions look like sort of the opposite of an operatic composition, right? If I take this surface over here and I give you the curve that gives me a Pants decomposition, alpha, it looks to you like, well, what did I do? I gave some composition which glued together these two blue ones. Right? Pants decompositions look like they should be operatic composition, and we'll argue that they are. And the same thing with a quilted Pants decomposition sort of also can be done if you add a little structure to your generating objects. Right, so if I take a Pants decomposition here, what do I have to give you? I have to give you some points here and here, and I'm not going to draw the scenes because this will be a disaster. But if I give you these points, what happens? Well, those came from now some generating object. And when I glued, say, this and this together, just to be contrarian and do it differently, I just made sure that those vertices glued up, and that would be, and the seams would sort of glue together naturally that way as well. And that would give me a quilted Pants decomposition as an operatic composition. Okay, so in fact, we can make this formal. So this is like an ongoing thing with Lucy Bonado, who actually knows how mapping class groups work. She's probably going to get mad that I said that. This is some ongoing joint work with Lucy about how we actually built a new modular operad. So this is a modular operad on seamed surfaces, for a lack of a better name. And what is this? This is going to be an operad in groupoids, a modular operad in groupoids. And objects are going to be surfaces. So with some canonical breakup into pants and quilts. So we're going to sort of impose, like make an atomic, like a choice of a generator with a choice of quilts, and then build surfaces in a sort of way like that. So this is where I'm saying I'm lying. I'm going to sort of not give you enough deep detail on some of these things to catch me lying. Just because it gets extremely fussy, but we will discuss more afterwards if you need them. Morphisms in this groupoid. Well, what are these? These are going to be homotopy classes of the orientation preserving diffeomorphisms, which preserve the collars. So this is collars. And the labels. I want to keep my labels. That's not how you spell label. The labels. Set. And so that's going to be what? Those are elements of the mapping class group of surfaces. So of this surface. And in fact, and I'm saying this here, but this is actually a non-trivial amount of work. So this requires checking. So I put these little arrows, and they're usually doing some heavy lifting. But the symmetric group acts freely on this groupoid, permuting the labels. And there's a homotopy equivalence of the classifying spaces. So B of SGN is the classifying space of the groupoid here, and the classifying space of the mapping class group. So I want to be looking at, I want to study the mapping class group because I want to study the fundamental group of the moduli space, because I want to study the moduli space. And now I'm going even farther, and I'm replacing it with another groupoid that I have a bit more control over, right? So what this statement here is saying is I'm going to use these groupoids, SGN, as like stand-ins for the mapping class group in my, okay. But these groupoids are nice. And if we use some of the techniques from that Hatcher and Thurston did to prove that the mapping class group has a presentation, we can show that this groupoid has morphisms, which are the composite of 3 elementary types of morphisms. One is a half Dane twist. So this is actually where the quilts are needed. So that's what this is part of. A half Dane twist means I'm just going to do a nice twist. So I'm not going to draw the quilts this time, and I'm going to show if I wanted to do a half Dane twist around alpha, right? Then I would just look at it like permuting the labels. And this would be sort of like, I would write this maybe like alpha 1/2. So I'm just swapping around. And that's something that's controlled by the quilting. So that's one elementary morphism. The second one is a really nice one, which is called A moves. So this stands for associative move. And it happens sort of locally on a surface of genus 0 of type 0,4, meaning that, you know, I could have a big surface, and if I'm looking at a Pants decomposition of it, I'm going to like sort of zero in on a particular piece of the Pants decomposition, which is of this shape, right? So this could be like connected to a bunch of other stuff. And an A move, so this is going to be something that takes alpha as part of my Pants decomposition of the surface. Make sure I drew this the right one, into beta. So here, if I label this, you can see that I'll write this as A alpha beta. Well, this diffeomorphism is sort of, it looks just like the associative relation. In fact, if you want to translate this down to trees, 1, 2, 3, 4, right? If I'm just saying this, it's a way to keep this in mind, what this move is. And the third type only happens locally. This is called S move, stands for simple move. I don't know what's simple about it, actually, but it's what it means. A simple move. And this happens locally on a surface of type 1, 1. So again, this could be like part of a larger Pants decomposition of some big surface. And here I'm taking a nice part of my Pants, I have a curve alpha, and it's going to this curve beta, right? So this is a diffeomorphism, and I'll write it as S alpha beta, where I'm taking this curve to that point. Okay, so these are my 3 elementary moves that make up all of the diffeomorphisms of the surface. So this is part of the proof of Hatcher-Thurston, right? We're using that. And in fact, they also show that these elementary morphisms, right, you can derive from their proof that our groupoid between these elementary morphisms has basically 6 relations between the morphisms. I've only put 3 here because we're only going to actually look at 2 later. I'll bring them back up later. One will be this one, and one will be this one. And what these are saying is that I am looking at the composite of these diffeomorphisms in the appropriate mapping class group. So this is living in, say, the mapping class group 0, 5. This is 1, 1. And this is living in gamma 1, 2. Okay. So I have some relations that all the morphisms in this groupoid have to satisfy. Okay, so that's nice, right? We have a nice like presentation, if you will, of the groupoid, or at least like some relations that have to exist on it. And a way to think about what's going on with this presentation, like what is this morphism saying? So the relation that we just had, and this will come up quite a few times, is that if you have this surface of, oh, it's already on there, sigma 0, 5, right? If I have this labeling, and I look at all the different ways in which I can cut this into pairs of pants, that they're all equivalent. That's going to be what the 5A relation said. And so I'll try to, this will be beta 1, beta 2. So if I'm looking at all the possible cuts, beta 3, beta 4, and beta 5. And so these would be the same betas in the relation that is drawn in the previous one. And because again, we're going to actually try to prove something today, so I want to make sure this is clear. So right, this A move where I have beta 3, 4. So what does that mean? That means if I took this this thing, and so beta 3 is going to be here. That means if I have a Pants decomposition of this surface, so I have to choose some other cut, I'll choose that one. When I apply alpha beta 3, beta 4, that means that I move to, yes, that guy stays there, and beta 4 is here, right? So that's what I mean. It's a local move, even if I draw them all on one giant figure. I'm talking about only the change of one particular Pants decomposition at a time. Okay. Questions? Everybody seems good. All right. So these groupoids form an operad, a modular operad. So you can define the cyclic I sub j, circ ij compositions, and the contractions. Basically, first you glue the surfaces on the objects, and then sort of the morphisms are the combination of the maps. They're the natural concatenation. So again, I'm ignoring quite a few details, and there's some work to be done here, so that this is actually well defined and associative. I'll just make one little note, because I think there's at least some people who've seen similar constructions. We do not include discs, like a copy of the disc, because that messes up quilts. So this is sort of it has no arity 0 operations that messes up quilts. Something to say. So this is a well-defined modular operatic groupoids, right? And these groupoids are going to sort of take the place of our mapping class groups. Okay. So I want to make a claim that this actually has something to do with GT. And so for the moment, let's specialize down to the genus 0 case, some stuff that's known. So like I said, I thought, I mean, I certainly know Geoffroy knows something similar to this, but because we're about to talk about some joint things, but other people have probably seen a very similar construction due to Aurikel Tillman. And this is in fact based on her construction. So if we specialize down to genus 0, and I'm going to have n plus 1. So I'm going to choose some like fixed boundary surfaces. So here, what I mean by with this red 1 is that one of the boundary components will be marked, and that will be the one that we're highlighting in red. Okay. And the other n components are free. So we're thinking of now having inputs and outputs. I'm going to specialize down even all the way to an operad. Tillman describes a groupoid, which she calls S0 n plus 1. And the objects are these surfaces together with sort of an atomic pan-C composition. So she doesn't deal, there are no quilts in her construction, but here, but you can add them. And the morphisms are, again, the orientation preserving diffeomorphisms that preserve the collars and the labels.
G is 0.
Gene is 0. Sorry, go ahead.
The question is G is 0 here.
Yes, G is 0 here. So yeah, we're gonna go to G is 0 for just a little while, so I can tell you about some results. Yeah, and so as before, and so sigma n acts freely on the boundaries, and you have this equivalence of classifying spaces between this groupoid of genus 0 surfaces and the mapping class groups. Yeah, and in fact, you can, so one gets an operad from this. This is what Tillman calls the surface operad, which is given by gluing. So you have your, oops, these red didn't show up as well as I hoped. So now with these marked points, this is just an operad. So I have a specified output. It is one of the free boundaries, and it looks like from this picture I've chosen, well, the blue doesn't show up. We'll highlight this guy, that one. And so you glue, gluing the red, the marked guy to that now pink one, sort of composing on the surfaces. I guess I can put like a little, the memory of that sphere is in this red. The fond memory of that sphere is this red dot now. All right, so, and it induces this is on objects, of course, but it becomes well-defined on morphisms and is an operad in groupoids. And here's one of the things where I'm being a little bit shady. So this is equivalent to the an operad in groupoids of parenthesized ribbon braids. So I'm going to tell you when I'm lying to you, but still do it anyway, which is that there's actually like a quotient, then you get to colored ribbon braids, then you take a cofibrate resolution to get parenthesized ribbon braids, and you end back up to sort of with had you never taken the quotient in the first place. So there's equivalent is like a heavy lie, but it's roughly the same thing. That's what I'm saying. You can get there just with some effort. Okay. Great. So yesterday I talked about this theorem of Geoffroy that says, you know, so remember these are standing in for our, I'll put it here. So like, remember, these are standing in for our mapping class groups, right? So we have these S0 n plus 1, these are our stand-ins for the mapping class groups, which are at that point are stand-in for the fundamental groups of the moduli space. So you're going to have to profinitely complete to get there. And this theorem of Geoffroy says that if C and D are two groupoids, and sort of part of the problem with my lies is the condition that we have finite sets of objects. So you have to be a bit careful. but that you in fact can do such a thing, and it works well with products, so that the profinite completion of this operad in groupoids is an operad in profinite groupoids. Okay. So now I have a claim. It's going a bit slow, I'll have to speed up a bit. There's an action of the Grothendieck-Teichmüller group, the profinite one, on this groupoid operad, on the profinite completion of S. Okay, and just a warning, like we actually prove something that's both stronger and slightly different, which is that you actually have an isomorphism of the profinite Grothendieck-Teichmüller group with, and this little sub-zero means like of automorphisms or endomorphisms of PARB, which fix objects. That's what the little zero means. Okay, but I want to talk about like just the action of GT because it goes with my story a little bit better. So I'm saying something weaker and a little bit different than what we actually have written in the paper. All right, so let's describe this action. So what do we have to do to explain how the action works? So I need to give you a homomorphism from GT to these endomorphisms that fix objects of the groupoid, of this operad in groupoids. Okay? Since I'm fixing objects, all I really have to do, so I'm going to have a particular object, so I don't need to tell you what GT does on objects. I want to tell you what GT does on the elementary morphisms. So, and we're down in genus 0. Oh, so I guess it's on, well, I thought it was all in one place. We're down in genus 0, so we only have 2 of these elementary morphisms. So we have the half Dane twist, and we have the A moves. There are no S moves because we don't have any of these tori. All right, so I'm going to define this action. So this action here, this is a known thing. This comes from, what I'm writing is in the form of what is in Okumura Schnapp's. It's easier, it's in several other places as well. So this action is a known thing, but the tricky part will be sort of to make sure it's an action for operads. This little n here, this integer that I'm not really going to describe. So this is determined uniquely by the quilt. So this is determined by the quilt and can always be computed. I just don't really want to tell you how. So it's not like it's undefined, but will depend on the particular object you start with. So it's also not the same for every object, right? It'll be different. Maybe in genus 0, it's almost always the same, but it will depend kind of on the chosen quilted Pansy composition. Okay, so what do we have to do to define an action? Right, so let's recall what our A move is going to look like, right? So here, this alpha goes over to beta. This is my A alpha beta, and I'm going to act on alpha beta by so this is a diffeomorphism, and when I write that alpha beta now and then I multiply times F A B, and then it was A N lambda minus 1 over 2, right? So first of all, what is this here? So remember this FAB, this is because there's a morphism from F2 into, now this morphism is living in the mapping class group here. So this is the FAB, where A is the generator. So this like corresponds to A in the mapping class group. This is the generator in the mapping class group corresponding to that curve. B is the generator in the mapping class group corresponding to this curve. right? So this is a word in A, B, living in the mapping class group. This is a well-defined thing. This is just a composite of elements in the mapping class group. Again, A here is the generator from that guy, and then N is determined by these quills. So all of this makes sense, is what I want to say. All right, and then so that the definition makes sense. Now we just have to check that it's well defined, right? So you just want to check that this action actually works with the relations that all the elementary morphisms have to satisfy. So what do? Well, you pick one. So here I wrote this 5A morphism down. And this is the kind of thing that doesn't translate well on slides. It translates extremely well on the board. You could just write it down. So what do? You act on the relation. So I'm going to act on the sequence A beta 3 blah 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 through A beta 5 beta 1 by my choice. Okay. I put dots here because it doesn't fit on the slide. And now in this case, and I'm not going to explain, what happens is that all of these integers n, so you can check, this can be checked, that n goes to 0 in all of these cases. So you can in fact kind of delete all these extra Dane twists here. So these will go away. And then, well, what happens next? Oh, I deleted my, oh, I just repeated it somehow. Right. That does actually look a little bit better though. So now you end up here and you pull the values of the, oops, no, it's actually the other way around. It's the right, I guess. So, right, this action is given by a group homomorphism. So in our case, group multiplication in the mapping class group is categorical composition. So these things commute, and you actually can pull these values away. And then what you have here, well, so now I have this sequence, my original alpha beta 3 to beta 4, and then I have this sequence here of words in F2 in various letters. So this is equal to 1, right, by the 5A relation, by the relation I started with. And now I've got here this sequence of words. So all you have to do is translate this, and you'll see that this becomes the third relation that I had in the definition of GT. So I won't draw all of them. Maybe I'll just draw one of them. So here, 1, 2, if I label these again. And well, what is B3? So beta 3 is this one. And B4 is this one. Beta 4 in here. So what does this mean? So here, FB3, B4, this is the one, so B3, if I act, what is that? That's the Dane twist that swaps 3 and 4. So this is just a translation. This is equal to FB3, B4. And you do this for all of these things, and you end up saying, okay, so this is also equal to 1 because this satisfies the pentagon. So this is the pentagon. Okay. So I know that's a quick and dirty thing, but it's sort of how is this action done, right? How do you actually do it in real life? So the actual action on the groupoids, by the way, is not somehow the hard part. The hard part is showing that it's compatible with the Operad compositions. But I claim that's a proof. All right. And then in fact, you can carry this over. And so we saw using the nerve theorem, this is just, again, using the nerve that we talked about a lot of times, but in this case for operads, that because we have the isomorphism of the automorphisms of S hat, right? This here, this is where I'm taking the homotopy classes of maps, and here N S hat, where is this living? This is living in, so profinite groupoids, diagrams over omega. So dendroidal, I don't know how to call that, dendroidal profinite groupoids. The dendroidal object in profinite groupoids is where this mapping class group is taken. And now you can actually, right, we talked about yesterday really briefly, well, when we take our classifying spaces, so remember these are supposed to be, this is, now we're getting closer to our mapping class groups. These happen to be nice. They're nice enough so that the proposition we talked about yesterday applies. And so you actually get here an isomorphism where now B and S, this is living in, so profinite dendroidal objects in profinite spaces, right? It's here. So this is like, this is an infinity operad. That's the point. And so, so this space is, now we're close to this sort of topological meaning that we wanted. We're looking really at the mapping class group. Okay, I can slow down for a second. So the spaces here, okay, this is actually technically not a lie, so that's okay. So these are all roughly equivalent, weakly equivalent. Well, maybe I didn't say exactly how, I didn't give you enough detail on these groupoids for this to not be a lie. It's not true. But this is definitely, this is fine. Right, so the spaces, if you take the classifying space of these groupoids, in this case, they're homotopy equivalent to the spaces of the framed little disks. So this is the framed 2 disk. Operad. And these are very closely related to the moduli space. This is the Deligne-Mumford compactified moduli spaces of genus 0 points, genus 0 with n marked curves, right? And what I mean by closely related is in this theorem of Gabriel Drummond-Cole, which says there's a homotopy push out of operads. So this is in the, this is of operads, where you have, it basically like homotopically trivializes the circle, right? It's a nice way to say it. So going down to here to the moduli space. And what we want to look at is, okay, so now we know if we look at this and we have an action here of GT hat, zigzagging through some homotopy equivalences, can we pull the action down here? So the first thing you have to check is that you can actually profinitely complete, oh, there's a missing hat. It's like a big hat there. So the moduli spaces are nice enough in genus 0, so that in fact this dendroidal profinite space is an infinity operad as well if you profinitely complete. And you can now sort of translate this diagram over into a push out of infinity operads, I guess is the way to say it. Yeah, I'm missing a giant hat here as well. It's a hat. And you end up showing that there's, well, now we have a non-trivial action of the profinite GT on this infinity operad. So this is, maybe it's not quite the moduli spaces, but it's certainly as close as we can get. And in fact, sort of the inclusion of the absolute Gauer group of Q into GT hat sort of acts on at least at the level of homology as we kind of want it to. At the level of homology. I think this is the thing I'm saying. So in other words, you can actually like go through this whole Operad rigmarole and get closely related to the goal of understanding how the Galois group, or definitely how GT acts on the surfaces, and hopefully learn something this way. Okay. Great. Pause. All right, so I didn't say anything today that specifically relied on that fixed boundary. And in fact, this sort of in progress, there's a cyclic version. Something that's just taken a while, and what's a fundamental thing I'll point out is, we really rely on the fact that we can look at, in fact, parenthesized ribbon braids. And then this is a nice groupoid. Not right. This parenthesized ribbon braids is just a much nicer groupoid than the surfaces, and it's easier to work with. And so we've been looking for a cyclic version. I know I talked to Paolo Salvatore about it a long time ago, and then there's one recently in the literature that I think is good. So we'll just put that as in progress. And I also want you to sort of, this will be a thing I mentioned in the higher genus situation as like a complication, right? Not having such nice little groupoids can be very difficult. Okay, great. So there are groups related to GT that sort of interact with our other groupoids, right? So I didn't go through all that quilting stuff just for fun. Well, I don't know, it's kind of fun. But yeah, that's not it. It wasn't just a hobby. So this is a definition of a group lambda from Nakamura and Schneps, and it's actually based on, there's also there's a version of it in an earlier paper. I should have added both here. Oh no, I think there's an A I'm missing. Hold on. Anyway, anyway, I'm gonna misspell his name. There's an A somewhere. I'll just put L and apologize later.
C-H-A-K, anyway.
Thank you. I knew there's not an A here though.
No.
No, okay. So, okay. So that tells you that I both mispronounce it and can't spell it, but and so there's an earlier version of this group in this other paper as well, and then but the version we're looking at is this lambda. And so this lambda, what is this? So this is the subgroup. Basically, it's adding an extra relation to GT. So it's pairs lambda F. They satisfy this same extra property in GT. And it satisfies the relations 1 through 3. So the symmetry, hexagon, and pentagon of GT. And in addition, relation 4, this new relation here, which is this giant nightmare equation. And I'll just point out a couple of things. So, so one thing, this row, this is a different integer. This is not like this comes from the Galois group. This is not like a twist. This is an actual well-defined thing. I won't tell you where it comes from. I tried to think of a quick way to explain it and failed many times. And M is lambda minus 1 over 2, shortened to make everything fit on the slide. So this is a relation now happening in the mapping class group of the twice punctured torus. Okay. And just to, I'm not going to write out all of these things, but just what are the types of diffeomorphisms that are happening here? So one of the, oops, that's not the pen. One of them might be something like, I think this one would be, we'll put it like that. Okay, this last little bit, okay. So I might have a diffeomorphism where this guy goes over to, say, here, right? This is the kind of relation that's happening here. So this would be A1, A3, E1, E1 in that language to correspond with what I've written there. Okay, so what we can say with Lucy is that there's certainly an action of this mapping class group of this group lambda on the endomorphisms of, now this is the big guy, so this is the modular operad. With all of the higher genus stuff. And this action is going to be given, so this, again, this is the action, this action comes from Nakamura and Schneps. This is not like something we came up with, but this is something that you can find there. And again, these ends are going to be determined by the quilts. And the row is something that, you know, is also, let's just say it's part of the data, but it's not something that I want to talk about. That's going to be coming from sort of lambda, not from the surfaces. So n comes from the surfaces and rho comes from lambda. Maybe is an easier way to explain what's going on. And these n are uniquely determined, but they will differ depending on the particular surface you're acting on. So just like before, because we're going to look at fixed objects, you know, these are the elementary morphisms. So we're just talking about how lambda acts on morphisms of at a particular chosen object. Okay. So just, I'll just do a quick idea of how this works. So the S move, right? Remember we drew this out as, well, this is going to be alpha goes to beta. S stands for simple. And when I write this action, so this goes, right, so S alpha beta is going to some giant thing. So I have ABA, I don't know, it's had some integers, some, and I'll just write some blah, 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 and then an F, A squared, B squared. So this actually makes sense. So this is an element that's central in the mapping class group here. And this is now here again, F, there's also a map from F2 into this mapping class group. That's not an F, that's a gamma. And here now, A is once again the image of alpha, the generating Dane twist coming from alpha. B is the generating Dane twist coming from beta. So this actually is all, this makes sense. It's a composite of diffeomorphisms in the mapping class group. Okay. And so now you just need to check that this is well defined, that it works with all the structure on the groupoid. So the relations of the morphisms. All right, and what do you do? So we'll just write out some sequence that comes. This is one of the relations I had that was 6AS. Well, 6AS literally means there's 6 things and they correspond to A and S moves. So I guess it's not that cryptic what that what that stands for. All right, so I'll just show you. You do the action. Like I said, this is one of those things that doesn't translate super well on slides, so sorry for swiping equations past you. As well. So here, right, what happens? You act on your A. You have this huge long equation. Then you go about and you compute each n. Okay, so there's a bunch of n's. This is going to depend on the object where you started, and so and they'll just I've reduced them in a way that makes sense here in the next thing. So you're just going to have to believe me that when the n's disappeared. And then you do the same thing as before. You pull all of the A moves and S moves away, and you end up with your isolated words and some other junk. But this turns out to be that that horrifying relation, right? So this is how you would do this action. Now, of course, again, this is the easy part. The hard part is checking that it actually works as a, there's actually an action on the Operads. So you have to check that it works with the Operad compositions, but we'll take that as a black box, and it can be done. In this case, we can do it directly. Okay. We don't have a bunch. Yep, there's a question in the.
See, you have a question on the chat.
Are they these? I don't know what you mean by computer generated. So these relations, they come actually directly from the work of Hatcher and Thurston. So I think they were done by hand. So where do they come from? You find them by looking at this thing called the maximal curve complex of a surface. So you build a complex, and each point is a Pants decomposition of a vertex is a Pants decomposition of the surface, and then the edges between them are sort of A moves, S moves, or you get like an infinite number of half Dane twists, which make it messy. And then, yeah, how did they, then they get the relations by, I don't know, being Hatcher and Thurston, I think was the answer. They fall out quicker, and when you read their paper, it looks easier than it probably was. But as far as I know, these relations all come from that. So it, yeah. Yeah, so it wasn't like, it doesn't take too much work. Okay, great. So we don't have all these nice homotopical relations yet back to the moduli spaces, and I expect something like it will come out, but I just wanted to point out, like, what is the difficulty actually in doing such a thing? So we don't have this nice thing with ribbon braids or braid groups, these nice little groupoids that you can rely on. It's kind of annoying. These are big. And the other thing that's a little bit subtle is that, right, when you move to profinitely complete classifying spaces, you have to be careful. Mapping class groups for genus G greater than or equal to 2 are not good. They're not nice. So you have to truncate and play games with your modular operads. So there's lots of truncation needed. But that's also not so bad. And then there are a few little homotopy theory problems which just need to be worked out for infinity modular operads. I say little homotopy theory problems, but they keep me up at night. So they're not great, but there's some stuff there. But I expect along the lines, eventually this will come out so that you can see the action on the moduli space. I won't make any claims about Galois groups though, because I still get very confused by that. All right, so that's one group related to GT. And with my 10 minutes left, which is still more time than I wanted to mention a different group related to GT. So I mentioned this briefly at the end of yesterday's lecture. And so I guess I don't need to mention it today, but it's on the slides, and the slides dictate what I must say in life, right? They were already written, so it's too late.
Can I
Yeah.
interrupt? So the conjecture you expect is that you get an isomorphism with this lambda in higher genus. You see, you had that GT hat was isomorphic to your S in genus 0. And
Yes.
now in higher
Yes.
genus, you expect that the lambda of Schneps and etc. Is, well, exactly, that's the conjecture you expect.
Yes, I expect this to be true. And this I'm not so worried. This is not like really the super hard part. And then hopefully something very nice might happen where you have an action on some kind of completion of this thingy. So this is the part where things are more subtle. Because there's you have to play around. So this is like, we basically have this written down. This part has some subtlety in it, and I just wanted to point out what the subtlety was like. Yeah, and then
Marcy, where do you need exactly infinity modular operads? And where
so
can
when
you stick with modular operads?
So this part, you can do this all with regular modular. So nothing really fancy here. It's only when you want to pass to the classifying space, when you want to look at like the classifying spaces of these groupoids and move toward the modular space. So you want to make some comparison with the topological things. Then you need infinity modular because because the profinite completion will only be sort of like weakly product preserving.
Okay, thanks.
Yeah, so this part can be, this can be stripped here. Okay, so and any more, because this is like I can pause, I can even add a whole page. You're good? All right. So there's another really interesting group related to, and now I'm going to drop out of profinite, so related to GT, but comes from like modular operads. So the relation is modular operads are here too. And this is this Cauchy-Verne groups. So this is no longer profinite. So to follow the notation of we've used so far, there's a little Q hanging out here. I don't know, there's some Q's everywhere, right? So these are the symmetry groups of the Cauchy-Verne solutions. So what this is, so right, these are what this diagram is. So as we saw already, that GT and GRT sort of are known to act freely and transitively on Drenfeld associators. And I've done something a little bit tricky here, and I've actually restricted down to a subgroup. So with this little sub 1 means I'm taking pairs where I've set lambda equal to 1. So that's what the sub 1 refers to in GT. Of course, all of GT acts on Drenfeld associators, but my diagram that I've gotten here has a 1 in it, right? And we're Drenfeld associators, so these are basically some solutions to equations, right, in these Drenfeld-Connolly algebras that Damien was talking about. And this is just a very similar problem that is happening now in Freely algebras on 2 letters. Sorry, maybe I shouldn't draw the hats because there's too many hats. These are just that just means degree completion. I'm being too pedantic for such an informal discussion. So these are solutions to equations in a Freely algebra. And Alexiev and Tarasian, oh no, this is gonna get terrible spelling situation. Showed that there is a map here. So every Drenfeld associator gives you a solution to Cauchy-Riemann. And they extended it over to define a group and a group map from the graded Grothendieck-Teichmüller group to this group Cauchy-Riemann group, I don't really know what to call it, that acts freely and transitively on solutions. And then in a later paper, Alexiev and then now Enriquez and Tarasian gave a similar thing for the non-graded side. So I have this nice big map, diagram of torsors here. That's what's happening. And they're closely related, right? So KRV and KV are closely related to GRT. Oh, there's a 1. And GT. And in fact, there's a conjecture in their paper. This is that KRV is isomorphic to GRT cross line. So they actually do this in Lie algebra form. So there's a semi-direct product there, but I'll just put being a bit sloppy. And similarly here, I think this conjecture was extended. So I'll put AET and AT for where you can find this. So in a recent paper with Zhuji Dansho and Eva Halacheva, we show that you can in fact compute these two groups as automorphisms of, so this here is a, these are W foams, and these are arrow diagrams. So these are like, so W foams are knotted surfaces in R4. So these are like knots, they live in R4. And arrow diagrams are a higher dimensional version of chord diagrams, which you've seen already this time. And these are both, so in the paper, we present them as a type of wheeled prop with orientation switches, which is equivalent to a non-connected modular operad. And I should just say that the reason that it's like this in the paper is Zhuji and Eva are like topologists, and saying that unoriented means the same thing as you can choose either orientation. Things got pretty intense for us on that kind of conversation about whether or not to say the word unoriented. So we chose for a very rigid thing to say, but it's really a non-connected modular operad. And I actually don't know if that has a name, like if it's like a prop or modular prop, seems like a terrible name. But that sounds like maybe it's a question for Martin Marco. He'll probably have a name for it. Okay, so there are modular operads happening here, and I wanted to conclude, as I asked yesterday for my question for the audience, you know, does the pro-finite version of this problem even make sense? I mean that as like an algebraic question, like I know what pro-finite GT means, but what would the other one mean? So I'm hoping there's someone in the audience that knows more algebra than me that can send me an email at some point. All right, great. I will stop there and do some questions. Oh, I think there was a slide. Thanks for listening to 3 talks of my rambling. So.
Sorry.
Thank you.
Is there any question? Well, il y a un peu de décalage avec l'Australie. There's some delay with Australia. Is there any question? Maybe you can come. Paolo has a question for you. He's coming closer to the microphone.
Okay. Hi, Paolo.
Just to make sure that about modular spaces and mapping class rules, because I think that you need modular spaces with some kind of tangent base if you want to relate them to the mapping class group, classifying space.
Oh, yeah, you do need to be, you mean when I had this sort of oh, this thing, and then if you want to have this related to this, yeah, you have to have some kind of yeah, some kind of tangent. Yeah, this is not a direct thing. So even right, even when we wrote down sorry, in the genus 0 case, right, we're not going directly here. This is homotopy equivalent to the framed disk space, and then you get here via this push out of Gabriel, Drum and Cole. So you go through some. Oh, and there's a bar there. So yeah, you do have to have some extra structure to make this really. There's not like a direct thing there that I'm aware of.
Without the bar, it's not homotopy equivalent. Yeah.
Without the bar, it's not an operad, right?
Well, it can become an opera in spectra, but it is another story.
Oh, really? That's that. Can you? That's really interesting. Okay, so could someone tell me how that works? Just for curiosity. Cool. That's a really cool thing to know.
Okay, anyway, just a remark that if you want the boundary to be preserved twice, then this corresponds to moduli spaces with tangent base. Otherwise, if you remove the boundary, then it is the ordinary, homotopy going to the ordinary moduli.
Okay, yeah. Did everyone hear his comment that if I want this to be related to if I want the classifying spaces to be related to the moduli space, there has to be some tangential base points or something. Sorry, otherwise you don't have this connection that I made. That was one of my lies, but thank you.
Is there any other question? Guillaume has one for you.
Okay.
Coming close to the microphone.
I feel bad that I have to make you guys walk up to the front of the room like you're in school.
Well, so yeah. So when you say is isomorphic to the endomorphisms preserving objects of PA RB who's completed, then you speak of endomorphisms of operads, right?
Yes. Yes, this is an endomorphisms of operads.
Yeah. Okay, and then the conjecture is that this lambda is isomorphic to the endomorphisms preserving base points of S. S is the entire set of modular spaces, right? You have all genus there.
Yeah, this is where so S hat here, this is this collection of all the groupoids here. And these groupoids are these sort of quilted pants. The objects are these quilted pants guys, quilted pants decompositions with morphisms and some rather rigid quotients that I observe. But they're, yeah, that's what that S is supposed to be.
Okay, and so then on the right-hand side, the object gets bigger because you take all genus instead of only 0. But on the left, it gets smaller because it's a subgroup, right?
That's right.
But okay.
Yeah, because so then if you have a bigger object, then the endomorphisms of it are going to have to preserve more structure, which ends up with a smaller group. That's the idea.
That makes sense. Thank you.
Thank you. Okay. I have a question. Could you show your last slide, please?
This one.
Perfect. So, as we were saying, maybe it was yesterday or the day before, Alexeyev, Kawazumi, Kuno, and Naev, they have higher genus and higher boundary components of KV. So they have KV N. See? So not only KV 03. So what is KV 03? And my question is, do you have any guess? I mean, if I'm considering the group KV GN, do you have any guess of how to realize that in the same way as the one you have? So out of something.
Not yet. Okay. So no, I do not have a guess. So this came about. So this came where these guys come from is from a low dimensional topology. This is from work of Barneton and Juji Dansho, which is the other co-author here. So and they do some weird stuff with knot theory, which is really quite operatic naturally. So they do something called circuit algebras, which turn out to be like these sort of wheeled props or modular operads, depending on some orientation thing. So that came from that connection. But as far as these higher genus KVs, I haven't been able to sort out how to deal with those surfaces with the curves, and I don't know. So
okay, good.
It's
see, when you think at the modular spaces of curves, they come naturally equipped with generalization to higher genera, etc. So that's why I was asking my question. Okay.
Yeah, no, it seems like that would be a much closer. That's when you brought that up. I feel that that's actually probably the answer to this question. If you make more sense of these KVs in terms of the moduli spaces with these, or these surfaces with the curves embedded, then this actually probably does make some sense. But certainly, as far as what these foams are, these are knotted objects in R4. I don't know. That wouldn't make any sense to me what a profinite version would be, for example.
Okay. Is there another question in the audience, in the world? No. So we can thank Marcy again for all these beautiful 3 lectures. Thank you very much, Marcy.
Oh, thank you.